So, in the last lecture we discussed about the damped free vibration model, where we said there are two kinds of damping. One is the Coulomb damping, which is based on the frictional forces, or the viscous damping, which is proportional to velocity. We already said why we follow viscous damping for ocean structures. Today in this lecture we will compare and show you why the Coulomb damping is comparably inferior with respect to that of viscous damping, but let us complete this discussion. So, we have this x of t equation 7, which we discussed in the last class. We found out from the complementary function for a given equation of motion, which is second order ordinary differential equation. We found out that it is a function of initial displacement and velocity. It depends on omega d, which is damped vibration frequency, which is a mixture of cosine and sine function, which you can try to plot. Now, the whole equation parenthesis multiplied by an exponential decay function, because there is e power minus zeta. So, if I try to plot this for different values of t, now the question is what value of t should I take? I must try to take a value of t in such a manner that the cosine and sine function will change their phase. So, obviously cosine sine function will change their phase at every pi interval. I started with 0, I said pi by omega d. So, omega d will cancel, only pi will remain, then 2 pi by omega d and so forth. We got a plot like this, which is time, and let us say this is my initial displacement, which we know, which I am taking as x naught. Maybe let us write it like this, we are using this way, say x naught and x naught naught as the initial displacement given to the system, and we know these values. We know this value, we know this value, we know this value. Let us write down these values for our understanding. This value was minus x 0 e to the power of minus zeta omega by omega d, let us say pi. Let us say this value is positive x 0 e to the power of minus zeta 2 pi omega by omega d and so on. So, if I call this as x 0, x minus 1, x 1, x minus 2, x 2 and so on so forth, because I say minus 1 is negative value, plus 1 is positive value, we would always see that in everywhere the x naught, the original displacement, is getting multiplied by a decay function, and it ensures mathematically that the response will come to 0. We can also say the decay is exponential by connecting the top or the bottom, because I can also give a minus x naught. It will be an exponential decay function. We can always say it is a decay because it is negative, it is exponential because e power. So, it is an exponential decay, and we all know in mathematics the exponential decay is much faster in decay compared to linear function. We will show that the Coulomb damping compared to viscous damping is much more inferior, because the decay is going to be linear, whereas it is non-linear here and is faster. As I said in the beginning that they are interested in finding out the zeta value. Now, one may ask me a question without knowing the zeta value, how this was plotted. This is actually a response obtained from the system using a sensor. You may keep an accelerometer, or you can keep a displacement transducer on a moving body, give initial displacement to the body will keep on moving, acquire the data and plot it like this. So, this is let us say this is an experimentally obtained plot, but my interest is not this, my interest is to get zeta, or at what zeta this will become 0. Okay, my interest to get zeta, which is the damping ratio. So, let us see how to get zeta. This is where we stopped yesterday, and this is what we plotted. I hope nobody has any questions on understanding this, we are able to get this. Okay. Now, let us try to find out zeta. Now, I will pick up two positive responses, two positive, I can also pick up two negative. Let us pick up two positive responses. Let us say the first response is x naught, that is what I am picking up from here. The second positive response, I call this as x 1, which is nothing but a multiplier of x naught with e power of zeta omega by omega d of 2 pi, or let us write it here minus 2 pi zeta. That is the value here. Let me find a ratio of this, that is x0 by x1. Now, what I am trying to do here is the ratio of successive positive displacement, okay? The ratio of successive positive displacement. Why I am not looking at the successive displacement? Because successive displacement has a phase of change, one is positive, one is negative, okay? So, the amplitude of this will be actually sum of these two. So, I am not interested in that. I want to know what would be in a given cycle, because we all know the cycle starts from here, completes and ends here, and so on. So, in a given cycle, what is the decay? So, I must look at the either the positive jumps or decay or the negative jumps of the decay, okay? So, I will look at the positive response. I look at the ratio. I can also do x1 by x0. Why I am doing this? Because we all know that is going to be a positive number now, more than 0, because x0 is more than x1. Why? x1 is multiplier of x0 with the decay. When you do this, I have an advantage. This negative goes to the numerator. So, it becomes simply e to the power of 2 pi zeta omega by omega d. That is an advantage why do this, okay. Now, I can take logarithm on both sides. I can take a Napier logarithm, which is natural logarithm on both. When you do that, it simply becomes 2 pi zeta omega by omega, because log e to the base e is 1. And we also know omega d, also omega d is omega root of 1 minus zeta square. Substitute back here, I will get the natural logarithm of is going to be 2 pi zeta omega 2 pi zeta by root of 1 minus zeta square. Now, the left hand side I call as logarithmic decrement. Why? There is a decrement because x1 is less than x0, it is a decrement. Logarithmic because there is a log value here. So, I will simply say this as the logarithmic decrement is simply 2 pi zeta by 1 minus zeta square, okay. Now, let us look at this equation. If you really wanted to know the zeta value here, I must know the logarithmic decrement of this. Now, if you are slightly intelligent, you can easily know, sir, I have this plot obtained from the system directly, therefore, I know these values physically from the plot. Therefore, the left hand side of this equation is known to me actually. I can straight away find zeta from this, okay. Now, the question comes, do I have to compare only the successive positive? Can I compare this positive with nth positive, this negative with nth negative? If I do so, what would be the significance of this in this equation? The first question comes, how this equation can be generalized, because this equation is only giving a decrement of successive positive amplitude. So, I must bring this equation in a general form. I can pick up any positive amplitude with that of the positive amplitude and include that value variable in my equation. That is number 1. Number 2, will it be different if I pick up this peak with an nth peak and find zeta, this peak with successive peak and find zeta? Will it differ? Because that is the second question now. If it is so, then how long should I take the value? Should I take the value till reaches 0? Then all these ambiguous questions has to be answered. So, for answering these questions, this equation must be generalized. Is it clear? I want to know the generalized equation. Now, let us pick up a generalized equation, but before that, let us try to see okay. Let x0 by x1 be e power 2 pi zeta omega by omega t. We know this. or e 2 pi zeta 1 minus zeta square. Now, let us quickly get into some exponential series. If I have e power x, how do I expand this? That x is the variable there. Okay, let me write it very clearly. This is e power. Okay, there is no multiplier here, all are exponential power. So, if I do this 1 plus x square by factorial 2 this is how it goes. Let me use this series of expansion here where x is this argument. I expand this. So, we know e power x is 1 plus x square by 2 factorial x cube by 3 factorial etc. Now, for lower values of damping zeta, because zeta is a damping ratio, we already said it is 2% or 5%, which is 0.02 or 0.05, they are very low. In that case, the denominator will tend to become unity. Okay. So, I can always approximate x naught by x 1 as e power 2 pi zeta. I can approximate this. Therefore, the exponential function x series can be 1 plus 2 pi zeta plus 2 pi zeta whole square by 2 factorial and so on. Now, for lower value of zeta, the higher powers of zeta can be neglected because the value of zeta is very low. Therefore, this can be still approximated as 1 plus 2 pi zeta. Now, I replace this equation on the left hand side as x n by x n plus 1. Please understand here, I am only still taking the ratio of successive amplitudes. I started with x 0, went to x 1. I can also start at x n and go to n plus 1. Okay. Still, this argument is as same qualitatively as this. Okay. Therefore, I write this as 1 plus 2 pi zeta. Now, the argument is to find out zeta. Now, it is very easy. If I know this value, I can easily find zeta as okay. I wanted zeta, I will get zeta now. Okay. Now, again the answer is, if I do not want to look at the successive amplitudes, I want to look at the mth amplitude, how do I generalize this equation to get zeta? Now, let us draw a curve and pick up the mth amplitude and generalize this equation quickly. So, write the equation here, zeta is xn plus 1 minus 1 of 1 by 2 pi. Let us say my plot is like this, which is x, which is t, which is response here, which is x of t, it goes like this. Please believe me that they are exponentially decaying. Okay. Now, I have this value with me. Let me call this as x 1. I have this value with me, which is x m. So, I must say zeta as a generalized form as x 1 by x1 plus m, or let us say xn. You can start from anywhere. Let us be xn, this is xm, xn n plus m minus 1 by 2 pi of m. Now, in this example, what will be the number m? So, leave this peak, start counting from the successive positive peaks 1, 2, 3, 4. So, m in this example will be 4. So, x1 by x5 minus 1 by 2 pi m4 will give you the zeta. It is very interesting for you to know that whether you pick up the successive amplitudes or pick up mth amplitude, zeta will not change significantly. Okay, not change. But it is very difficult for you to get a system which is having a decay with a very long cycle. This indicates system is highly elastic. Generally in offshore structures, systems being very stiff and rigid, you will not even get more than 2 cycles, okay, because they are very stiff. They will come to response, dead end of the response very quickly, because offshore structures are designed to come to response, which is called a recentering capability, as quick as possible. So, you cannot expect a large number of cycles for to come to response dead, it will come quickly. Therefore, you will have no opportunity except using the successive peaks in finding out zeta. Therefore, it is very clear and evident in the literature that even if you use zeta with mth peaks decaying, quantitatively zeta will not change significantly. Okay, that is a property of the exponential decay actually. Okay, mathematically it will not change much. So, we can find out this simply, this peak is known, this peak is known, I get the ratio, I simply subtract this and use this equation and find the value of zeta in percentage. This will be a number, multiply with 100, you get zeta. So, this is how zeta is worked out for. Now, with this zeta if you plot, you must get back either this equation or this figure or this figure from the original function, which is equation 7. Okay, that is how it is done. Any doubt here? So, we discussed damped free vibration system. Now, one may ask me a question, if the vibration is free, where the damping source is coming from? Damping source can come from hydrodynamic, can come from air. Okay. It also the system is enabled to design to a recentering configuration, therefore, damping is present in material, in structural member, in the environment. There are various sources. So, you will not be able to get the damping of different sources separately from this equation. It will give you the overall damping of the structure. Okay. If you really wanted to know from this what is the component of hydrodynamic, what is the component of material, what is the component of material degradation and member degradation, you will never get. That you have got to do separate analysis for this. We can do that, but this equation is highly generalized, which we are interested in. We wanted to actually know what is that ratio which brings the damping or the structure to rest. We are interested in that. Within that, what is the contribution of different elements will be of intrinsic research interest. But in general dynamics, we are interested to know, is it becoming to 0? Yes. How many cycles? Known. What is the value? We know the value. So, we are answering all the questions almost which are unknown in the given equation, but zeta is one of the unknown in the given equation, because if you do not know zeta, you cannot find omega d. Omega d is a function of zeta actually. Okay, you cannot find this. So, you do not know what is the damped vibration frequency at which the system is resonating or oscillating, we will not know. So, we need zeta. So, what generally people do is they do not conduct experiments to get zeta, they assume zeta, which is recommended in the structural systems as 2 to 5%. You can take any value. Somebody asks why have you taken 2.5, you can give a justification, provided you can conduct an experiment and show my zeta is close to 3, I have taken 2.5, and so on so forth. Remember, it is a structural characteristic which is derived from an experiment. Therefore, this will have all errors, including the experimental boundary conditions, experimental context, scale value, material property, because concrete can be damped very quickly, whereas elastic cannot be, and so on and so forth. Be very careful about making this statement when you give a research proposal. This will include all in one. you cannot find separately from this equation. There are methods which we will not touch in this course. Okay? We will stop here now for the moment, then we will move on to the next topic. So far we have discussed about damped forced free vibration. Now if the forced vibration is present, what would be the change? Mathematically what would be the change? So before we answer this, let us try to ask why Coulomb damping is not effective in offshore structures. We have seen the viscous damping is exponentially decaying, therefore it is effective. Let us talk about Coulomb damping. Coulomb damping is a damping developed between two surfaces because of friction. A typical plot of Coulomb damping will look like this. Now, since damping force is opposite to the response, generally there are negative damping also. Generally the damping force will be opposite to the response because it has to bring down the response to the equilibrium state or neutral value. So, it is negative in comparison to that of the kinetic energy of the system. Now, let us see what is the total energy present in the system in a frictional damping like this. We all know that the work done by the mass should amount to 0. So, let us say what is the work done by this mass. One is half kV square, which is the kinetic energy where we do not have velocity, initial velocity is 0. So, we do not have the kinetic energy because velocity is 0. We have a restoring force which is kx square, k is the spring stiffness, therefore, I write here as x1 minus x minus 1 square. That is, if you call this as x1, I will call this or this value, let us say as x minus 1, I call this value as x2, I call this value as x minus 2 and so on so forth for the legend. This is the restoring force minus the damping force which is arriving from the damping, is negative because it is opposite to the response. Now, this will be the total displacement in a half cycle. I am looking only the half cycle. So, I should say x1 minus of x1, minus of minus, so becomes plus, looking for the total amplitude for a half cycle. Why it is half cycle? I am using only x1 and x minus 1. I am not using x1 and x2. I have used only x minus 1. So, it is half cycle. Which will be of course set to 0. Now, we simplify this, which is given as half k which will become half. Okay. Now obviously this cannot be set to 0 because you have a value. So I will set this to 0. So x1 minus x minus 1 is twice f d by k, which is linear. For half a cycle. Now I can extend this as x minus 1 minus of x 1, that is the second half, is also going to be similarly 2 f d by k. Therefore, x 1 minus x 2, this dk, which is this value, will be 4 f d by k. 2 f d by k dk here and further 2 f d by dk here. Okay. So therefore, if you really wanted to know that this should be set to 0, you must do that many number of cycles to become this 0, because the decay between the successive cycles is fixed as a linear function. So this will take a long number of cycles to decay. It is because of this reason Coulomb damping or frictional based damping is not admitted in offshore structures. Let us move on to undamped forced vibration. We already know the essential characteristics are m, k, c and f of t. The system without m and k is not possible. They are always omnipotent in every system, because system should have a restoring force, that is the recentering capability in the design. System should have a mass. If the system does not have a mass, even though the acceleration is very large, inertia force is low, we do not have to do dynamic analysis. So mass and k are always present in a system if you really want to do dynamic analysis. C may or may not be there, f of t may or may not be there. In this case we say undamped force. So C is set to 0, f of t is present. So let us draw the system. Single degree freedom system, idealized spring mass model. There is no dashpot here because C is 0. So undamped. I can draw Newton's motion for this, which is kx, which is mx double dot. So mx double dot will be equal to minus kx, which should be force into acceleration. So mx double dot plus kx is 0. But I have a force additional, but in this case is going to be some f of t. I will take this function as some amplitude with some frequency, where omega is called frequency of the forcing function. So now this has got two solutions. The right hand side is not 0. Therefore, you got two answers here for this problem. One is the complementary function, other is the particular integral. Let us do both for this. and try to sum them up and see how the solution looks like. So, let us say mx double dot plus kx is 0, that is my auxiliary equation. I say d square plus omega square, because k by m is omega of x is 0. So, d is plus or minus omega I. So, complementary function can be x of t, which is e power alpha t a cos beta t plus b sin beta t, where alpha is 0 in this case, beta is omega. Now, to clarify, there are two omegas here. One is the omega which is coming from the system with a natural frequency which is nothing but root of k by m, which is appearing from here. There is another omega which is the forcing function frequency. We have to differentiate these two for our nomenclature. I will substitute all these values as omega n. N indicates natural frequency, which is a system property. Omega indicates forcing frequency, which is not a system property. Okay. So, just to differentiate in our mathematics, otherwise you will get confused. Now, I write complementary function x of t is a cos omega n t plus b sin omega n t. There are two unknowns a and b, I can evaluate them as a initial condition. Now, let us go to the second part of the solution, which is the particular integral. So, particular integral is the second part of the solution. The right hand side is p0 sin omega t by d square plus omega n square, that is what I have in my equation. And you will appreciate that the equation of motion is mx double dot plus kx is p naught sin omega t. I divide this by m, I get x double dot plus k by m of x is p0 by m of sin omega t. I say this is x double dot plus omega square x is p naught by m sin omega t. So, I should not write p naught here, I must say p naught by m. Okay. There is a m divider here. So, let us say pi is going to be p naught by m sin omega t, that is the argument d square plus omega n square. We all know to solve this, because if I have a function which is here, what I should do is I must say d square s minus omega square. As long as the denominator does not become 0, I can solve this, is it not? If it becomes 0, you differentiate the numerator and keep on doing it until the denominator should not become 0. That is the rule to solve a particular integral. I am going to do the same thing here, p naught by m sin omega t by minus omega square plus omega n square. Now, we really do not know whether it becomes 0 or not, because we do not know the values of omega and omega n, we can leave it as it is. Okay. I will rewrite this slightly in a different form, which I say p naught by m sin omega t. I will take omega n square out, 1 minus omega by omega n the whole square. Omega n square is k by m, we already know that k by m is omega n square. So, I substitute here p naught by m sin omega t, k by m 1 minus omega by omega n square. I go away, it becomes p naught by k sin omega t by 1 minus omega by omega n the whole square. So, therefore, my x of t, I expand this and write it here. My x of t is going to be, which is the response of the function which is undamped forced vibration, will be a cos omega n t plus b sin omega n t plus P naught by k sin omega t by 1 minus omega by omega n square. I want to eliminate A and B as usual. So, at t is equal to 0, x 0 is the initial displacement and x dot 0 is the initial velocity. Let so let us differentiate this x dot of t minus a omega n sin omega n t plus b omega n cos omega n t plus P naught by k omega cos omega t by 1 minus omega by omega n square. So, let us substitute these conditions in these two equations. So, at t is equal to 0, this term will become simply a, these two terms will go away because it is sine function. So, I will get x 0 as a. Now, at t is equal to 0, substituting in the second equation, this term will go away. So, it will become x dot 0 as b omega n plus P naught by k omega 1 minus omega by omega n the whole square. Therefore, I can easily find b as x naught 0 by the whole argument minus of this and so on. Let us say I have the value of b with me. Let me write down the full function here. So, x of t after getting a and b will be x 0 cos omega n t plus x dot 0 by omega n. I am splitting these two terms separately. Minus p 0 by k there is an omega n multiplier here. So, when you take it this way, this will get divided here. So, I should say omega by omega n, because this omega n will get divided here because this is a sum here divided by 1 minus omega by omega n square of sin omega n t plus p 0 by k omega cos omega t by 1 minus omega by omega n the whole square. Sin omega t. Even here also, yeah, sin omega t, sorry, it should be sin omega t. P0 by k sin omega t by 1 minus omega by omega square. Actually picked up this term from the velocity. So, let us check x naught cos omega n t, x naught by 0 omega n minus p naught by k. Okay, the argument of sin omega n t is for the whole, okay, because that is b sin omega n t, b is the value which I got from here, plus p naught by k sin omega t, so on. Let us discuss about this equation. I call the equation number 8. There are some interesting discussions on 8. Let us see what is that. The equation 8 has got 2 terms. Why? There are 3 terms, but I will put them 2 terms, because one term is a function of natural frequency, the other term is not a function of natural frequency. You may say, sir, this term also has omega n here, okay, that is a ratio, but ultimately the multiplier is only omega. So, 2 terms, one term or the first term is a function of natural frequency of the system, the second term is not a function of natural frequency of the system. That is first difference or first observation I have. The second observation, the first term depends on the initial conditions of x naught and x dot naught. The second term does not have initial condition dependence. So, dependence of initial conditions. Suppose I say initially x naught and x dot naught are 0, they will not exist, but this term will always exist. Okay. The one which is dependent on initial condition and a function of frequency in natural system is called transient vibration. The one which does not depend on natural frequency of the system and which is not dependent on initial condition is called steady state. Now, the response has got 2 components, transient response and steady state response. Now, one may ask a question, why this response is called steady state? This response is called steady state because this response will always exist in a given system. This will only diminish when there is no P naught, where P naught is the amplitude of the forcing frequency or the forcing function. So, if you do not have a forced vibration, this term will not be there, which was not there in equation 6 and equation 4 respectively. It is here because you have got a forced vibration given to the system, which is omnipotent, always present. Therefore, this response will always be present, that is why it is called steady state. Okay. Now, interestingly, in this equation 8, if the forcing frequency becomes matched with the natural frequency, the function will become infinity. Okay. But I cannot handle that in the mathematical solution here, because look at the Pi, sin omega t by d square plus omega n square is the Pi. If I say this is omega n, I cannot solve the Pi in the same form as I solved in this equation. Okay. Therefore, the solution drawn for omega not equal to omega n, which is given by equation 8, cannot be substituted by simply saying this is omega n, this becomes 1, infinity and so on. No, cannot be done, because the procedure for solving a particular integral when these two are equal is different from this. Mathematically we cannot do that. Okay. Therefore, to get back to the same equation where resonance will set in, I look at this whole concept slightly in a different form called dynamic amplification factor. That is so in structural dynamics, the whole concept of resonating frequency is expressed as a ratio of beta, where beta is the ratio of the frequencies. Let us see what happens beta becomes 1, okay, from the same equation. Strictly speaking, if beta becomes 1, the equation should not give me an answer, because it will become infinity. Steady state response will become infinity, is it not? Should not give me an answer, right. Let us see how. Do we have any questions here? So, in this lecture we have discussed about two things. One, we have compared Coulomb damping with that of the frictional or viscous damping, and we understood why Coulomb damping or frictional based damping models are not effective for offshore structures, though there are dissipation of energy or damping arising because of friction of between two particles or two members in any joint in an offshore structure, because the decay is linear, take long number of cycles to decay, whereas in instantaneous response steady centering capability is required in an offshore structure. Therefore, in reality when they are designed like that, we must adopt a damping model which is proportionate to the real behavior which is coming from viscous damping, number 1. Number 2, we also understood from this lecture how to get zeta if I have an experimental plot of a decay of response, how to get zeta for n number of peaks. The third case we already understood, in a given forcing function available in a given system, though damping may not be present, undamped system, there are two kinds of classically explicit response coming out from the total response. One is a transient response, one is a steady state. Transient has got specific characteristics, steady state has got specific characteristics. Steady state will always be present, that is why it is called steady state, transient will not. Now, one may ask you a question here, is the transient response not important? Why do we actually handle this? Can we only deal alone with steady state? The answer is no, because in offshore structures unfortunately, talk about fluid structure interaction, the transient responses like springing and ringing play a very major role to cause instability. So, transient response also becomes important in offshore structures. Friends, offshore structure is the only one classical system which is where transient response is considered to be important. There is no other system except offshore structural system where transient response is taken as a study in dynamics. People generally ignore this. Okay. Here it is important because springing ringing, we will talk about this in module 2. I will tell you how this becomes important, which can cause instability to a platform even though transient steady state response may not be important. Okay. So, very important, we cannot ignore this. So, generally people neglect this, they say it is not important and so on and so forth, but that is not the case in offshore structures. Okay. So, we have learned the summary now, we will close the lecture now. If you have any doubts, kindly post it to announcement forum in NPTEL. Thank you.